Alright, time for the math. Easy solution here to discuss basically introduction to higher derivatives. What I mean by this, if you have a function, let's say y is equal to f of x, and basically the derivative or the rate of change is just y prime is equal to f prime of x. But if you were to do derivative, let's say of this, because this is a function, we do derivative, we get this. This is also a function. So if we take derivative of this, we just go y, well, it's double prime, is equal to f double prime of x. So all we do is take derivative twice. And another way of writing this is if you could also write the derivative as dy over dx. This is as well as equal to df of x over dx. So basically derivative in terms of dx, change in y over change in x or whatnot. But then if you do double derivative, you just go d of this entire thing over dx. So then this is the same thing as writing that way, dx. So you just take derivative of the whole thing, and you can also write it as d2 dx of f of x, and this basically signifies that it's a second derivative. So let's look at an example. So basically, let's say example 1. Let's say y is equal to x times cos x, and we want to get, let's say, y double prime. So basically we first do the derivative initially, so we go y prime is equal to, we'll use a product rule. In this case, this is going to be basically derivative of x is just 1, so we're going to have cos x plus derivative of cos x, which is negative sine x. So negative sine x, and then we just times by x. And then if you take the second derivative, so basically what this is basically this is the rate change of this function. So now the second derivative is just the rate change of this function. So we're gonna have y prime double prime is equal to, well, just whatever derivative this one is, negative sine x. And then plus the derivative of negative sine x is just, well, negative cos x, or derivative of sine is just cos x, so we'll have negative cos x using chain rule. Just put the whole thing in chain rule, and this is going to be times cos x, and then this is a plus, or we'll just go minus sine x times derivative of x is just 1. So we get, basically it's going to be negative, so everything is negative, negative sine x plus, this is actually 2 sine x. Add these together, negative 2 sine x plus cos x times x. Or you could just write it as negative cos x minus 2 sine x. And so basically this is just the rate change of this, and this is the rate change of this one. Now I'll show you a good way of, like in a real world application, basically what this second derivative can be. So basically we have this example. Yeah, so basically this example is, let's say you have the position of a particle, or whatever is given as s is a function of t, where t is in seconds, s is in meters, so basically s is equal to t cubed minus t squared plus 9t. So this is a position of a particle, basically. And now let's say if we were to solve these examples, I got this example from my calculus textbook, it's pretty useful. So let's say find the acceleration at time t, and what is the acceleration after 4 seconds. Basically, if we look at A, acceleration is we know that acceleration is equal to, well, basically the change in velocity, dv or dt, where velocity, and then we know that velocity is basically equal to the change in position, or change in distance, or whatever, with time, so ds over dt. So basically this is similar as taking, basically, if this is ds over dt, this is also equal to s prime, or the derivative of s prime, and this one can be written as, basically, we know that v is this, so we'll have d over dt of ds over dt, and this is also written as, basically, as double prime, which I just showed above. So basically this acceleration is second derivative, and this is just first derivative. So this is a real world application, basically. So now if we were to find acceleration at time t, well, we need to get the velocity. So basically v is equal to s prime is equal to well, 3t squared, just take derivative of that using power rule. 6 times, well, bring the 2 down, and then t is power rule again, plus 9. And this simplifies to basically 3t squared minus 12t plus 9. Okay, so now to get the acceleration, let's do derivative again. So s double prime is equal to a, and this is going to be equal to, well, just bring 2 down. This is 2 times 3 is 6, t minus 12. So there's our acceleration at any time t, as it asks here, at any time t. Basically, this is a straight line, it's an equation of a line. And then acceleration after 4 seconds, so basically at t is equal to 4, we're going to get 6 times 4 is basically 24 minus 12, so we're going to have a is equal to, well, 12 meters per second. Per second squared, if this is the units. Basically, if s is in meters, then velocity is change in s over change in t. This is basically meters divided by seconds, so then v is meters over second, and then acceleration is change in velocity over change in seconds, so a is just going to be equal to over s, or equal to m meters per second squared. So that's meters per second squared. So now let's look at part B. What is part B? This part B, graph the acceleration for graphs between 0 to 5 seconds. Well, this one we'll just use a Google graphing calculator, which is pretty amazing. Let's bring it up. Okay, so if we just drag in the Google calculator, let's just put in the functions here. t3 minus 6t squared plus 9t, comma, just put in the velocity now. 3t squared minus 12t plus 9, and then if we put in the acceleration, 6t minus 12, then you can also do this from this is 0 to 5, so it automatically puts it where we want it. So basically puts it from 0 to 5 here, and now let's just make this zoom it out a bit so we can see it a bit better. So basically this is how the graph looks like. This is the distance one. Basically it's going, the distance is getting up here, then it goes back down, and it goes all the way up here. So basically that's how it would look like, and this is your parabola, is this red one is the velocity. So the velocity is basically, it's saying is that it was going fast, it's slowing down, it was going backwards, and then it goes back up. And acceleration, what is saying that this initially it was slowing down here, and the acceleration is negative, so it was actually slowing down, and then it's going faster up. Okay, so now I just took a screenshot of that photo right here. Okay, so here I just took a little screenshot here. So basically this one, this is the distance, or s, that's s, and this is basically acceleration, let's call this a, and the red is velocity. So basically that's our graph, and now let's look at this equation, the question C, which is one is the particle speeding up, one is it slowing down. So basically C, okay, so one's particle speeding up, other slowing down. What this means is basically if you have a particle here, if its acceleration is increasing in the same direction. So let's say if you're going forward like this, and you're going faster and faster. So basically if you're going faster and faster, this means that basically your acceleration is basically it's increasing, or you have your acceleration is increasing with your velocity. With velocity, what this means is if you were going forward, let's say you're moving forward, going forward. So if you're going forward, or v is positive, then you would be speeding up if your acceleration is positive, and you would be slowing down if your acceleration is negative. This is slowing down. Or if you're going backwards, so if you're going backwards, then your velocity is negative, and the only way you could be speeding up is if your acceleration is negative as well. If it's positive, that means you're actually slowing back down. So it has to be a negative. So basically, if the signs are the same, then you're speeding up. If they're opposite, then you're slowing down. So then if we were to look at here, so basically here velocity, this is a distance. So basically velocity, you are basically positive here, from here to here, and you're negative from here to here. This is negative, this acceleration is negative. So this is, you're actually slowing down because those signs are opposite. So you're going to be slowing down. That's actually slowing down from these 2 points. Let's go from here to here. And then in this case here, your velocity is negative, or you're going, so this means negative, so your displacement, you're going back to the original position. Because see, as you can see, that you can just look at this curve, it's slowing down here. It's the rate of change is slowing down, of the velocity is slowing down. And then if you hear it's actually, your velocity is negative, or you're going back down, but this is actually still negative here. So this entire place is negative. If you look at acceleration right here, this is actually speeding up. You're speeding up, going back to zero, speeding up. So it's speeding up. This is just the direction has changed. So now here the velocity is positive again. I mean, this acceleration is positive here. So then this means you're accelerating in the positive direction while your velocity is negative from here to here. So you're actually slowing down. You can just tell by the way it curves. If it's like curves like this, it means it's slowing down the distance one. So slow down. And then at the end here, your distance, displacement is going through the roof there, and your acceleration is positive. Your velocity is positive, so you're just speeding up positive now. This whole thing is speeding up. Yeah, so basically you could just tell by just the signs. So if V and A have same signs, then this is speeding up. And if they're opposite, then they're slowing down. So that's all you gotta know. Well, this is all for today. Hopefully you learned basically higher derivatives. You could, if you take the derivative again of acceleration, you might have be just basically that's all it is, a derivative of the acceleration. And then you could apply it and whatever. There's other applications for that, but let's show that next time. But thanks for watching. Hopefully you learned, and stay tuned for another Math Easy solution.